which is also reproducibility talk. And again, about BPR. Aleksandr Milogradskii. Okay, this is revisiting BPR, a replicability study of a common recommender system baseline, please.
Yeah. Back. Yeah. Hello, everyone. My name is Aleksandr Milogradskii, and today I want to tell you about our research paper revisiting BPR, a replicability study of a common recommender systems baseline. Let's start with our motivation. Inspired by recent reproducibility papers, we decided to re-examine a well-known baseline model, Bayesian Personalized Ranking, or in short, BPR. While BPR's widespread adoption has led to numerous third-party implementations, many of them lack essential features, leading to inconsistencies and suboptimal performance, which was also shown to impact other models as well. Additionally, many studies using BPR as a baseline omit a detailed description of its implementation and crucial components. However, it has been shown that careful tuning of hyperparameters in linear models can bring their performance close to state-of-the-art methods. All of these issues highlight the potential need for a thorough reassessment of the BPR model, which was surprisingly absent in numerous influential reproducibility papers. First, I'll briefly introduce the BPR model and discuss its internals. BPR is a popular version of the matrix factorization model with a pairwise objective function. This model has attracted significant attention, evidenced by an increasing number of references, making it one of the most cited papers in the field of recommender systems. The pairwise objective in BPR aims to minimize the log likelihood of the correct ordering using equation 3 on this on this slide, yeah. 4 key characteristics apart from the model's objective and its structure influence this algorithm's performance. These are regularization, negative sampling, optimizers, and user item biases. Our study extensively analyzes all of these components, showing their impact on the model's behavior. Additionally, user item biases is an addition to the original algorithm, but it has been proven beneficial for many other recommender systems models. Additionally, item biases component is present in various open source implementations of BPR. We conduct our experiments to address the following research questions. First, how do the results achieved using open source implementations of BPR compare with the originally reported results? Second, how do the BPR model's features help to improve its performance? And third, how does the fine-tuned BPR compare with the originally reported results? Sorry, it's for some reason switches. What's going on?
Having issues with the clicker?
It switches automatically. I don't know why. Like I don't press anything and it goes next. Is it okay?
Yeah, I think it's okay.
Okay. Yeah. So where did I stop? Yeah. To address the following research questions, we conduct our experiments using various open source implementations of BPR, which are shown on this slide. I want to highlight 3 key insights from this table. First, in most BPR implementations, learnable item biases are present. Second, most of the implementations utilize uniform negative sampling. However, there is a better method called adaptive negative sampling, which according to the authors of BPR improves performance. And third, most of the implementations apply regularization using a single regularization factor rather than a 3-factor approach outlined in the original paper. Moreover, this table shows that only the Elliott implementation fully incorporates the complete set of features from the original paper, while the other implementations deviate from the complete set, leading to performance drop-offs in some situations. Notably, our implementation also includes all of these features and is written in PyTorch, making it easy to include in common experimental pipelines. It switched again, and I didn't click anything right now.
Is there any issue with advancing the slides? It should just be the clicker.
I don't know why, but just now it just switched to the next slide and I didn't press anything. And it happened multiple times.
He's going to take a look at it.
Yeah. Sorry. No, it would work, but for some reason it switches automatically. I don't know why. Okay. I didn't click anything. Okay. Yeah. And I didn't finish that one? Yeah. Additionally, given the significant time and effort required to fully experiment with all available implementations, we narrow down the list based on popularity and level of support. We focus on top 5 implementations in each category, underlined in the table. As I have already mentioned, for the first research question, we attempt to reproduce the results of the original paper. We conduct our experiments on the Netflix dataset, following the same evaluation protocol as in the original paper. This slide shows the model's performance with the default hyperparameter values based on ROC, area under curve metric. Notably, only Kornak, Elliott, and Dow implementation reproduced the original paper's results. In contrast, other implementations such as LightFM and Rigball demonstrate unstable results depending on the embedding dimensions. We attribute this instability to the adaptive optimizers used in these implementations. In the experiments for research question 2, we follow the strategies from the Revisiting Implicit ALS paper on the Movie-Lens 20M and Million Song Datasets. For each dataset, we find the best embedding dimension and then the best search of features. This slide shows the grid search of possible BPR hyperparameter values. It's important to note that the full grid search would have resulted in over 5,000 models for a single embedding dimension, which is too much. To simplify this process, we categorize hyperparameters into 3 groups and conduct experiments sequentially. These groups are item biases and regularization, second optimizers, and third negative samplers. This approach allows us to reduce the number of experiments by up to 5 times. Additionally, to further simplify the exploration of embedding dimensions, we perform a rough estimation of the best embedding dimensions using open source implementations of BPR, which is shown on the right. The best results are achieved using embeddings of size 512 and 1024, which are used in subsequent experiments. Now let's move to the evaluation of hyperparameters. Table A shows that the best results on the Movie-Lens 20M dataset are achieved using the model without item biases and with 3-factor regularization, just like in the original paper. In contrast, on the MSD dataset, the model with 1-factor regularization performs best. This finding suggests that the BPR regularization should be adjusted based on the dataset. Now, shifting our focus to optimizers in Table B, it's worth noting that only ADAM and standard HGD algorithms deliver satisfactory results, while the other optimizers struggle to learn effectively. Notably, adaptive optimizers succeed after reducing the corresponding weight of momentum vectors. However, even with this change, standard HGD algorithm still mostly outperforms adaptive optimizers. Negative sampling methods are tested only with ADAM and standard HGD optimizers with their best hyperparameter values from the optimizer group. The key finding here is that the models with the adaptive negative sampling train significantly faster and achieve better results. For instance, on the Movie-Lens 20M dataset, the HGD optimized model required 265 fewer epochs. And lastly, for the final research question, we conduct our experiments using 2 evaluation protocols, a user-based split and a global temporal split. The table on this slide compares the performance of various BPR implementations against the baselines on these datasets. Our solution with the best hyperparameter values, according to research question 2, demonstrates strong performance across all datasets. With proper hyperparameter tuning, we gain over a 10% improvement in the model's performance compared to other open source implementations of BPR, achieving a statistically significant first and second places on several datasets. Additionally, while the model with the ADAM optimizer also performs well, it is statistically outperformed by the model with the HGD optimizer on MSD and Yelp datasets. Concluding, we conducted a thorough analysis of the BPR model, successfully reproducing the results of the original paper. We also analyzed open source implementations of BPR, highlighting their differences from the original paper and assessing how these differences impact the algorithm's performance. Moreover, we carried out a detailed hyperparameter analysis of this model. We showed that with proper hyperparameter tuning, BPR performs on par with state-of-the-art methods across various experimental approaches. Furthermore, our implementation delivered exceptional results on datasets with a global sample spread. We hope this work will help other models utilizing pairwise adaptive function from BPR. That's all I wanted to say. Thank you.
Thank you for the talk. Do you have any question? Just a quick one, we're running out of time. So I get that you were able to reproduce the original implementation, and you also looked into efficiency compared to the other available implementations. So what's your final message here? Should the other ones be discontinued in favor of yours or maybe Elliot's?
No, absolutely not. Actually, we even make plans to add improvements to these implementations as in the form of merge request. Yeah, absolutely not.
And your implementation is available online, right?
Of course it is.
Okay, thanks a lot. Let's thank the speaker again.
Thank you very much.